Hey, so we're going to talk about the atom today. We're looking at these little teeny tiny particles that make up everything. And as we continue to understand more about them, we actually can start to make some properties or some predictions as to how they're going to start to interact, how they're going to start to form bonds and reactions and all that good stuff. But we got to start at the ground level. At what are these atoms? How are they built? And how can I describe one type of atom from another type of atom? And so as we think about just the general features of the atom, we've had a lot of people do a lot of work here. Atom is a neutral sphere. It's got no charge overall. That has a positively charged nucleus. That would be the center. That is then surrounded by a negatively charged field of or cloud of electrons. So in the center, we got all the mass. So our protons and our neutrons. And all around that, we've got this field of negatively charged electrons. And so if we actually, I heard a great analogy once upon a time. If your nucleus was the size of a pea, a little green pea, and you took that pea and you put it on the center, in the middle of the 50-yard line, the electrons, the closest other thing, the electrons would actually be in the stands. They'd be in the spectator stands. That is how much distance there is from that center to our closest neighboring electrons. Mostly empty space, which is crazy to think about, but that's what we got. Cool. If we dig in a little deeper, then we got three subatomic particles. Of these three particles, we've got the protons, the neutrons, and the electrons. Protons, P+, I'm sure you've heard of these before. Get the symbol P+. They are located in the nucleus, so right there in the center. They've got a positive charge, and they have a mass of 1 AMU. AMU stands for atomic mass unit. It's kind of a system we came up with for describing the relative size of our atoms. AMU is defined as 1/12 the mass of a carbon-12 atom. So carbon-12 is made of 12 protons and neutrons, 6 and 6. We said, oh, 1 AMU is one of those. We kind of made it up, but it lets us compare the sizes of all of our different atoms. We call it the atomic mass units. We had to come up with something because they were so small. We don't have a mass unit for that small of a particle. So cool. Protons, P+, they have both mass and charge. That's important. It's the only one that does have both mass and charge. Because neutrons, which get the symbol N with the little knot, N naught, are neutrons, also located in the nucleus, but they don't have a charge. They're neutral, which makes sense. Neutrons are neutral. They also have, so they have no charge, but they do have a mass of 1 AMU. There are other mass particle, 1 atomic mass unit. This makes sense. You got to have them in the center to actually help with the stability of the atom. If you had a bunch of positives all right next to each other, they would push each other away. So what we do is we kind of add these neutrons in between to make it so that our protons don't rip the nucleus apart, which happens in nuclear reactions. Different thing. We'll talk about it later. So neutrons, located in the nucleus, they're neutral, have a mass of 1 AMU, which leaves us just our electrons, which are zipping around in these little energy levels, which we'll talk more about as well. These are the ones that are important for bonding because they're out there in the outer shells. They're the ones that interact with other things. Electrons have a negative charge, and they're so small we say their mass is approximately 0. Compared to the protons and the neutrons, they're about 2,000 times smaller than a proton or a neutron. Very little of the mass actually comes from the electrons themselves. Cool. If we think about what holds the nucleus together, I'm going to flip through this one pretty quick. I would not worry about this so much. This is more for our folks that are interested in quantum physics or quantum mechanics. There is a strong force that holds the nucleus together. There's interactions between all the protons and neutrons. They are technically made of smaller things, subatomic. Quarks and leptons, these are things that exist. If you want to talk about them, come see me. We are not responsible for those. We're just going down to those subatomic protons, neutrons, and electrons. Cool. We got to have some way to start to rate these to show our different types of atoms. And the way we do that is what's called our nuclear symbol. Our nuclear symbol is comprised of a couple of different things. The X here in the middle represents the element symbol, which can be found in the periodic table. It's how we denote our different types. The top number is, let me get them all up here. The top number here is the mass number, which is protons plus neutrons. If protons have a mass and neutrons have a mass, we add those together, we get the total mass. And that's what the A value represents, the mass number. I always think of the Fonz, kind of an old joke, but he's A, mass number. This is your protons plus neutrons. The Zeiskev, I believe, is the original German. So Zia, was Dexter's laboratory, right? DD, stay out of my laboratory, DD. The atomic number. The atomic number is Z equal to the number of protons in an atom. So Z stands for the protons. This is actually how we identify elements. So when you go to the periodic table, that big number at the top of the square, do I have any handy? Oh, I do. The big number at the top of the square on your periodic table is the number of protons. It's our number one way of identifying one type of atom from another. So it's the atomic number. Cool, down here you'll see two carbons. Two carbons, they have the same number of protons, but their mass is different. The only thing that would account for that is the number of neutrons. We give this a name. We call these isotopes. Isotopes are atoms of the same element with different masses. Same element, but with different masses. So protons are the same, neutrons are not. And if we wanted to do the math, we actually can just subtract, right? 14 minus 6 gives us 8. This carbon has 8 neutrons, while this carbon, 12 minus 6, has only 6 neutrons. So extra neutrons doesn't change it chemically, because neutrons are neutral. Doesn't have any effect on the actual chemical behavior. Just changes its size, changes the mass of our carbon. Cool, so again, isotopes, same atomic number, so same number of protons, same number of electrons. The only thing that's different are the neutrons, different number of neutrons. Sometimes you'll see these written kind of funny. So here we've got N dash number. This dash number is the mass. So here's nitrogen with mass 14, nitrogen with mass of 15. Everything else is the same. We've just changed the number of neutrons. The other way we can change our atoms is by changing the number of electrons. Ions are what we give is our name for a charged atom, which I will argue most of the things we interact with are technically ions. Anything in a compound has been charged, unless it's covalently bonded. So ions, charged atoms. This means that their protons and electrons are not equal. They're different. If you wanted to find the charge, you take your number of protons and you subtract by the number of electrons. If you have more protons than electrons, you're going to be positively charged. If you have more electrons, more negatives than positives, you'd be negatively charged. We give a couple special names, a couple vocab terms here. An anion is a negative ion. That means you've gained or have extra electrons. If you have a cation, that means you've got a positive ion. You've lost electrons. Can't change the number of protons, though. If you change the protons, you change the element. Can't do that. We're either going to be gaining or losing electrons. The way I remember it is onions make you cry. Anions are negative. There's also an N right there in the word, a negative N ion, negative ion. Cation, got a plus sign right in there, right? The T is a positive sign. Also, cats have paws. Cations are positive. Whatever works for you. Just a couple of vocab terms that we need to know. Cool, so as we think about the structure, as we think about the different ways we can change, we got different names for atoms, isotopes, ions, changing neutrons, changing the charge. Good vocab that we need to be familiar with as we start to describe these atoms, start to think about how they're gonna react with one another. Cool, thanks for getting these notes today, guys. We'll keep layering as we go.